Analog meters for measuring current, voltage, and resistance can all be built without any digital electronics. And so here's how. First, an ammeter is a device for measuring electric current, for measuring amps, hence ammeter. And the symbol on a circuit schematic for it would be a circle with a letter A for amps in it. So there's an ammeter. And an analog version of this could be built from a little coil of wire, which when you run current through it will generate a magnetic field. A magnetic field that can be used to deflect a little magnetic needle. So here's a picture of one. When we run current through here, through this coil, the magnetic field that the current generates will deflect this needle to point towards the current that's flowing if it's calibrated. So we read off the current from the needle deflection here. Here is a realistic ammeter. I say realistic in that it includes some internal resistance right there, little internal resistance R. And so if this is the direction of the flow of positive current to the right, then the potential difference along that path, V final at A minus V initial at B, will be just due to that internal resistance. So minus IR, a little drop down that little waterfall as we go from B to A. Now, let's see here. In an ideal ammeter, what you want is that insertion of the meter to measure the current between A and B should not alter the current between A and B. But if our ammeter has some internal resistance here, then by inserting this device between points A and B, that internal resistance, that's going to change the total resistance of the circuit, which is going to change the current flowing through here. And so you don't want to change the thing that you're trying to measure. You want to just measure what it was before you inserted the meter. So that leads us to recognize that a very good ammeter, an ideal ammeter, is one that changes the internal, that changes the resistance, that changes the current as little as possible. So we don't want it to introduce any potential difference between A and B. We don't want it to have any internal resistance. The ideal ammeter has 0 internal resistance. That's what you're going for. Now, a real object will have some resistance, but you want to minimize it so that inserting the meter between 2 points changes that current as little as possible. An ammeter you can think of as like a toll booth that you insert between 2 points on a current, between 2 points on a wire, so that every electron passing through that ammeter gets counted. To measure the current, you have to physically go through that ammeter. That's different than how a voltmeter works. A voltmeter for measuring voltage. Here's the circuit symbol for that, a circle with a V for volts in there. And to measure the potential difference or voltage between 2 points, B and A, in a circuit, rather than insert the meter directly between those 2 points, as you do with an ammeter, you have to put that ammeter right in the path, as if it's a toll booth on the road, counting the electrons or counting the cars that go right through. With a voltmeter, instead, you set it up off to the side in a sort of a parallel branch, a side branch, around the part of the circuit whose voltage you're trying to measure. Okay, so here's a picture of a voltmeter with these red and black leads. And this X in a dotted box here is meant to represent some device in your circuit. And if we want to measure the voltage across that device, meaning we want to measure the potential difference between points B and A, we want to place, say, the black lead here in contact with point B. There's the black lead, and the red lead here in contact with point A. And so our meter in this dotted box here is off to this side in a side branch, a parallel branch, circling around device X right here. All right, so again, contrast that with the ammeter, which is inserted directly in the path of the current, not in a side branch, not in a parallel branch off to the side. Well, putting the meter in like this can enable us to measure that voltage as follows. Let's see. Suppose there was originally a current running through here, I naught. We want to insert the meter here in such a way that we change the current running through the device as little as possible. We don't want our measuring device to alter the thing we're trying to measure. And if we alter the current running through device X, then we're going to alter the voltage across device X. We don't want to do that. So with the meter in place, it will inevitably change the current entering the device at least a little bit. So let's call this the new I naught entering that junction right here. Some of that current will continue on through device X. We'll call that I1. Some of that current will be diverted through the meter. Call that I2. Then that I2 will rejoin I1 at this junction over here. And the new, so sort of reforming the new I naught, which will head out to the right over there. What we want is for our meter to disrupt the current through the device X as little as possible. In other words, we desire that current 2 be approximately 0. We want to draw very little current through our meter so that all the current continues to go through device X as it was before we put the meter in. So in other words, we want the original I naught to be very close to the new I naught to be very close to I1, so we have minimal interference. Okay, at our junction, we can write that the new I naught entering that junction will be split up into I2 and I1. And then the potential difference between points A and B can be found by taking either a path through device X or a path through our voltmeter. So we start at B and end at A. No matter which path we take, the potential difference, V final minus V initial, should be the same thing. So if we go through the meter, and our meter here is just our ammeter from above, we have the same device, a little coil of wire with some internal resistance. Now we just put it off to the side instead of directly in the path of the current. So the potential difference along this path will be just a drop due to that little internal resistance. So minus I2R minus I2 times that internal resistance. Or if we go through device X, then our voltage drop will be minus I1 times the resistance of device X. So this equals minus I1 times whatever resistance device X has. Okay, so then according to that relationship, we see that the current through resistor, the current through the meter, I2, equals the resistance of device X divided by the internal resistance of the meter times I1. And we already decided that we want I2 to be as small as possible, which tells us here that to minimize I2, given some Rx here that we cannot change, what we want is to make the internal resistance of the meter as big as possible. In other words, whereas an ideal ammeter had 0 internal resistance, an ideal voltmeter is just the opposite. For an ideal voltmeter, we want infinite internal resistance. Here we want this resistor to be very high so that minimal current is drawn off through that high resistance branch. We want all the current to continue taking the original path so that our meter doesn't disrupt it. Okay, so if you're using a digital meter like this one, a digital multimeter, there will be a switch to switch it from voltmeter mode to ammeter mode. And what that switch, one of the things that switch is going to do is change the internal resistance. One setting will have 0 or very small internal resistance if you're using it to measure current. And another setting will have very high internal resistance for when you're using the meter to measure voltage. But in any case, an analog meter like this can work just fine. Let's see, just to be clear then, the way you would actually use this device to measure the voltage between A and B, this little needle here would allow you to read off I2. Oh yeah, and here we go. If you know the internal resistance and you read I2 off that little meter there, then the product of those numbers tells you the voltage between A and B. There you go. That's how this analog meter can be used as a voltmeter. You read off the current that you draw, the tiny current that you draw here, because you want it to be small, and multiply that by your big resistance right here. And that's the voltage between those 2 points. So there you go, your analog voltmeter. Lastly, an analog ohm meter for measuring resistance in ohms. So that circuit symbol for that is a circle with an omega in there for ohms. So suppose we have some device X whose resistance we want to measure. So we'll put device X on a path. We will connect our ohm meter to either side of device X, similar to how we use a voltmeter. So we sort of connect it on a parallel branch to device X here. So connected from points A to B. This time, however, we don't want any current flowing through device X. We're going to remove device X from any circuit that it was a part of, and we're going to add in a power supply to the meter itself. So now our ohm meter has a little coil with a needle and some internal resistance and its own power supply to drive a current through device X just for the purpose of measuring the resistance of device X. So driving that current through, this current I driven by the power supply aboard the ohm meter itself. If we then follow a path starting from this corner here, a path all the way around the circuit, we call this a Kirchhoff loop. If we start here, we go with the current, so we drop down in potential through that resistor. The coil we treat as ideal. And then we go up in potential across that EMF. Then we follow the current and we drop in potential as we go through device X due to the resistance of device X, which then gets us back to where we started. So the sum of those changes should be 0. So starting from the top left corner, we drop in potential minus IR. Then we go up by the EMF. Then we drop in potential minus I times Rx, Rx being what we're trying to measure right here, which gets us back to the corner where we started. So that hike sort of goes down in elevation, then up in elevation, and then down in elevation again. So back to where we started. Down, then up, then down, and back to where we started. This tells us that our EMF is related to the current that the power supply drives and the total resistance, that is Rx, which we're trying to determine, plus the internal resistance of our ohm meter. And rearranging that to solve for Rx, we see how we can use the device to measure Rx. This will equal the EMF divided by the current minus the internal resistance. Yeah, so with our device here, if we know what the EMF is, and we know the internal resistance, and we read the current off of our little needle here with the coil, so we know this, and we read the current off, we can therefore determine the resistance of device X. So there's an analog ohm meter right there. And note that in this case, the internal resistance doesn't have to be very high, and it doesn't have to be very low either. It can be anything. As long as we know what it is, we can subtract it off and measure that internal resistance. We don't face the issue here of the meter altering the resistance of the device. The meter can't alter the resistance of the device. It always is what it is.